So in this video, we're going to be looking at a scenario where we have two concentric cylinders, one with the inner radius Ri, and then one with the outer radius, and wow, that was a terrible cylinder. Outer radius, big R, and then there's some fluid in between here. And we're trying to prove that if this inner cylinder is rotating and this outer cylinder remains fixed, we're trying to prove that the inner torque, the torque on the inner surface here, is equal to the torque on the outer surface. And we have some equations here. The first is for the velocity distribution. This W here is an omega. My omegas are just really bad. I'm not going to go ahead and say all of that, but this constant K here that is used in the velocity distribution equation is simply the ratio of the inner radius to the outer radius, and we can rewrite that in terms of the inner radius as Ri equals K times big R. Then we have the shear rate. The shear rate can be defined as R, or a given radius, times the derivative of the velocity function divided by the radius with respect to the radius. So our goal here is to define the shear rate using this expression. So we're going to start off with V theta. Oh, there we go. And the first part we're going to take care of is this V theta divided by R. So for the most part, this omega k squared over 1 minus k squared is going to stay untouched till the end, just because it's a constant. So we have omega k squared 1 minus k squared. And then we're dividing by r here, so we're going to have r squared divided by, well, big R squared divided by little r squared minus 1. And then from there, we just need to take the derivative with respect to r. So we have v theta over r equals omega k squared 1 minus k squared. And then the derivative of a constant, which would be the case with these two if you were to multiply them through, is obviously going to be 0, so we don't need to worry about that. And then r squared over r to the third. We had a 2 here before, so that has to be a negative 2. Then from here, all we have to do to get the shear rate is multiply by the little r, the given radius, which is going to be equal to omega k squared 1 minus k, nope. Brain says one thing and my hand does another. 1 minus k squared. And then, actually, let's go ahead and move this minus 2 out. And I'll fix that formatting in a little bit. And then we have r squared and then little r squared. Let me add, see if I can find, there we go. I gotta add more space here on this page. All right, so from here, we want to find the shear rate. Resetting my pen here. The shear rate at R is equal to Ri, which is going to be equal to omega k squared over 1 minus k squared. And then big R squared over Ri squared. And if we go back to our k equals Ri over R, we have Ri is equal to k big R. So we have Ri squared here. So we'll go ahead and replace that with omega k squared 1 minus k squared. And then, oh, I forgot the negative 2. R squared over k squared r squared. These cancel out. These k squareds cancel out. So we have the shear rate at inner radius I is going to be equal to negative 2 omega over 1 minus k squared. So from here, we can define torque as the force times the radius, and in this case it's actually going to be the inner radius. We'll do the same for the outer radius in a second. And the force can be written as the shear stress times the area, and the shear stress is equal to our shear rate times the viscosity of the fluid. So substituting in, we have torque at R is equal to Ri is equal to shear stress times viscosity times our radius times A from over here. So I need more space again. Let's see if it'll actually give it to me. It did. Wow. So again, substituting in, we'll start with the mu in the area. Mu times the area is going to be, so if we have a cylinder, it is going to be the area of this surface times the, well, not the area, it's going to be the circumference of the circle times the height, and that'll give us the area of this surface. So we have pi r times 2 to find the circumference times the height. And then we have that, so there's that. We have to multiply through by Ri. And then we still have sigma, but we'll come back to that in a second. And we can do the same thing with our torque at R is equal to big R. It's going to be the exact same thing, but instead of Ri, which I forgot over there, it's going to be big R. So mu times 2 pi big R times height times big R times sigma. All right, so from here, we're going to substitute for sigma, or our shear rate, using the equation we came up with up here. So for R is equal to Ri, we have mu times negative 2 omega over 1 minus k squared, and then 2 pi Ri squared times height. And then we're going to set that equal to our torque at R equals R, because again, we're trying to prove that the torques are equal. So we have mu times negative 2 omega 1 minus k squared 2 pi big R squared times height. From there we can cancel out these omegas, and I forgot that, oh no I didn't, and these h's. So we have, or actually, and these 2 pi's. So we have it's equal to negative 2 omega over 1 minus k squared little radius squared. 2 omega over 1 minus k squared large radius squared. In the correction here, before I go any further, this equation down here is not correct, because if we go back up to our sigma r equals ri, and we take this equation here before we went ahead and substituted anything, if we swap out this ri with big R, we're going to get negative 2 omega k squared over 1 minus k squared times big R squared over big R squared. So we're just going to be left with negative 2 omega k squared over 1 minus k squared. So we'll actually need to substitute this in back for that sigma. So down here, this is going to need a k squared, and then here it's going to need a k squared. So let me rewrite that just so it's a little neater. All right, so from here, we also have times big R squared. So from here, with some more canceling, we can cancel out these minus 2 omegas because these are constants. Oh. Ri squared over 1 minus k squared equals r squared k squared over 1 minus k squared. And as we know before, k equals the ratio of the inner to the outer radii. And so we have Ri is equal to k times r. So this can be replaced by Ri, and there we have it. The torque at the inner radius on the inner cylinder is going to be equal to the torque on the outer cylinder.